Hi everyone, this is Marley Miller, and today what I want to do is I want to talk to you guys a little bit about electron configuration, because that's something that is tripping some of our students up in chemistry. As we start to deal with electron configuration, one thing that we really have to be conscious of is something called quantum numbers. So there are several different quantum numbers. In fact, there are going to be 3 of them. And each one is going to be referencing a different part of the electron configuration. So the very first one that we're going to look at is something called the principal quantum number. Usually when we talk about principal quantum number, that's like the main one. So if you have like a principal issue, it means it's like the main issue that you're going through. So what is the principal quantum number? Well, first, oftentimes we are going to abbreviate that as N. So that's a good thing to know. And then what this principal quantum number is the main energy level occupied by the electron. So where are those electrons actually located? And the values for N are always what we call positive integers or positive values, such as 1, 2, 3, 4. In our case, what we end up having in chemistry is we have the numbers 1 through 7, and that would be because we have 7 rows on the periodic table. So when I go ahead and I look at this diagram right over here, I can see that my nucleus is right in the middle. Level 1, which would be N number 1, is the first level or the closest one. Then we have level 2, level 3 is outside of that, and because we have 7 rows of the periodic table, there are going to be 7 levels on the periodic table. A good thing to notice is that as N increases, the distance electrons are from the nucleus increases, and the electron's energy increases. So if I look here, I have level 3 versus level 1. So if I go level 1, they are close to nucleus, low energy, versus level 3, farther from nucleus, therefore they have higher energy. So that's our first principal quantum number, or first quantum number, which is the principal quantum number, which literally is just identifying which shell is that electron in. The second quantum number that we're going to be looking at is the one where we talk about the main levels being divided into something called sublevels. So the second quantum number is called the angular momentum quantum number. I honestly have no clue why this is, but it's abbreviated as L. Like, to me, that makes no sense. So we have our N value equals our level of orbital, like 1, 2, 3. And then we have our L, which is our angular momentum, which is going to talk about the shape or type. This one is going to be a letter, and it's either going to be S, P, D, or F. So when I start looking at our code here, we are going to have different levels. So we have our S orbital. S orbitals are going to be the smallest, so they can only hold 2 electrons. So when you look at an S orbital, like the 1s, the 2s, or the 3s, they just look like a single box. And inside each box, you can have 2 electrons. So we could have an electron like that, an electron like that, and we'll just talk a little bit about what that is in a little bit. Next up we have, helps if I have a highlighter on, is the p orbital. P orbitals can have up to 6 electrons. Therefore, instead of just having 1 box, they are going to have 3 boxes, because you can fit 1, 2, 3, 4, 5, 6 electrons there. Next up, we have the D level. It can hold 10 electrons. So when we look at a D level on here, we're going to see that up here. And you have 1, 2, 3, 4, 5 little boxes. So you can fit 10 little electrons in here. The last one, which is the largest one, is going to be the F orbital. It's going to have 14 electrons. Therefore, it's going to have 7 boxes. So this is just describing how big or small, essentially, the actual orbital is going to be. Again, this is called our angular momentum, or our L. So if I want to know what the L is for a p orbital, it would be 6, because I can fit 6 electrons in there. If we're looking on the periodic table, this shows you all of the different blocks. Remember, when we go from smallest to largest, we have our S, P, D, and F. S blocks can fit 2 electrons, P can fit 6 electrons, D can fit 10 electrons, and our F can fit 14 electrons. So this actually makes quite a bit of sense, because when I start looking, if I look at my S block, notice the S block takes up 1, 2 columns, and it also takes in the helium, because helium, if we put it in its right spot, would actually sit right there. So 2 columns, 2 electrons, so it makes sense why the S orbital can fit 2 electrons there. Next, when we go to P block, we know that P block can fit 6 electrons. Let's look where that's located, way over here. And if we count, we have 1, 2, 3, 4, 5, 6 columns that make up the P block. So if you have 6 columns, it makes sense that all 6 are going to go into those 6 columns, right? Those electrons there. Next up, our D block. Let's count. We know we can fit 10 electrons. You think there's going to be 10 columns? Probably true. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Heck yeah, that's our D block. And then last but not least, we have our F block. It's probably going to have 14, right? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. So that makes perfect sense. So you can tell based on where they show up in our periodic table where their blocks are going to be filled up to. So if I know that I have, if I want to look at something like this particular element right here, I know that in order to get there, I had to fill that, this, and this to get to that point. Here's another example that shows you the numbers, the principal quantum numbers, or the n numbers ahead. So here we say that this is the 1s, and this is also a 1s because we can fit 2 of them in there. 2s, 3s. Notice that these numbers are increasing as we go down. We have our 2p, 3p, and so on. It looks a little weird that we have a 4s and then we go 3d, but that's just how this one works out. And then our F block, notice it's 4F that actually fits in right here. So that is another good one to know. The last quantum number that's important for us to remember is the spin quantum number. The spin quantum number is going to tell us about the orientation of the electron's magnetic field relative to the outside magnetic field. So that sounds a little bit weird. Really, what we're looking for is the spin, or the spin of the electrons. We know that 2 electrons that are negative are going to repel one another, and when we have opposite spins, we allow those two to come together and they can be in the same orbital. So what we say is they get a positive half spin or a negative half spin. The other way of showing that is just as arrows, as either up or down. Another thing that you can do instead of doing a full arrow is, I'm super lazy and I just do a half arrow like that for up and a half arrow like that for down. So that means the exact same thing. So a single orbital can hold a maximum of 2 electrons. So this is pretty important. I'm going to highlight this. A single electron can hold a maximum of 2 electrons, which must have opposite spins. So if I start drawing out some orbitals, when I put electrons in there, the only way they work is if we have one up, one down. If you have two up, they repel, so that's bad. And if you have two down, they also repel, so that's also bad. The last thing I want to teach you a little bit about is with electron configuration, how we are going to fill these. So electrons are going to fill orbitals that have the lowest energy first. We always fill these in the same order, so it's really, really nice for us. The smaller the number in front equals the lower the energy. So we're going to use this little thing. You guys have probably seen this in Buzz already. But what this is going to do for us is, I always say follow the yellow brick road. So I use yellow arrows to show this. And when I do this, you go and you fill the 1s first, and then you start looping back, okay? So next up we fill the 2s. Then we loop back and we fill the 2p, then the 3s, then the 3p, 4s, 3D, 4P, 5S, and we just keep coming back, and that's how we're going to go through. So this, the 7P6, would be the last orbital filled, okay? And you get to stop whenever you run out of electrons. So we'll do an example of that in just a second. The last little rule that we have, remember, we have to have the lowest energy being filled first. We have to have opposite spins on our electrons. But our last one states that orbitals of the same quantum level are occupied by one electron before any pair occurs. So what does that mean? Well, let's start looking at these. Here we have lithium. Lithium is number 3 on the periodic table, therefore it has 3 electrons. So I can tell it has 1s2, meaning there's 2 electrons there, and only 1 electron in the 2s. So I fill my 1s first because it's the lowest energy level, so 1 up, 1 down. And then I'm going to put 1 in the 2s because that's all I have. Beryllium has 1 more electron, so I'm going to put my down arrow in there. Boron has 1 more, so it has 1 in the p orbital. So I'm going to put that guy there. Here's where this Hund's rule comes in. Carbon has 1 more electron than boron. Instead of pairing it here, we're going to give it its own spot. So think about if you had like family come into town and all of your extended family were staying in your house, right? You'd probably want to put 1 person per bed before you start pairing people up in a bed, right? So each person gets their own room or their own bed first, and once you run out of room, now you start pairing them up. Then you pair another, and then you pair another. So that's how Hund's rule works. So what we have here then is we're just going to go through an example problem. So write the electron configuration for an atom whose atomic number is 17. Okay? So what I have to do is I'm going to start by going to my smallest value first, and I'm going to say 1s. If we think back, remember S, P, D, and F are the orbitals. S can fit 2, P can fit 6, D can fit 10, and F can fit 14. So I have an S orbital, and I can fit up to 2 in there. So I'm going to go exponent 2. So that's meaning in the first orbital, that first quantum level, I have an s orbital which can fit 2 electrons, and I'm going to fit both of them in here. Okay, so I have my 1s2. Then I'm going to follow my road. The next one I can go to is the 2s. So I'm going to go 2s. And how many can go in an s orbital? Well, it's 2. So at this point, if I add these, I know that I have 4 electrons taken care of, but I want 17, so I'm not done yet. So I'm going to keep going. Next up, I'm going to go 2p, and I can fit 6 there. So now 6 plus 2 plus 2 is 10. I still need 7 more. So then what I'm going to do is I'm going to go to my next one, which is the 3s, and I can fit 2 of them in there. So now I have a total of 12 electrons that I have. So we're getting closer. And then I'm going to go and I'm going to follow this and I'm going to go 3p. I know it can fit 6, but do I need all of those? Again, I have 12 right now because I have 2, 4, 10, 11, 12. I need 17. So I actually only need 5 in this. So I end up with 1s2, 2s2, 2p6, 3s2, 3p5. So that's the electron configuration. I'm going to go in blue here, and I'm also going to do orbital notation. So I know that 1s has one box, so I'm going to draw this as a line. This is my 1s. It has 2 electrons in there, so I'm going to go 1 up, 1 down. Next, I'm going to write my 2s. Again, I know an s only has 1 orbital, but can fit 2 electrons. My next one is a 2p. 2p can have, it has 3 spots, and when I fill it, I'm going to go up, up, up. Then I'm going to go down, down, down. Remember, it's like sharing beds. You don't want to have to share your bed, but if you have too many family members, maybe you have to. So don't share the bed until you are running out of beds. Then we go back to the S, 3s, 1, 2. And then we go 3p, 1, 2, 3, because that's a p orbital. So 3p, and I need 5 of them in there. So I'm going to go 1, 2, 3. Now I'm going to start pairing them, 1, 2. Notice we could fit one more there, but we don't have to right now because it's a 3p5. If you have any questions, let me know. Otherwise, have a great day.